Another topic is graph theory. What is a graph? What is the definition of a graph? Actually, the graph is defined as GEV. A graph is defined as GEV. It is very much important to computer science and engineering department because in computer science there is a topic like data structure. Okay, for data structure there are so many structures are there, array, stack, queue, and so on. Graph is another data structure. Graph is another data structure. Which one is suitable for graph? Which data structure? If the objects or things are in hierarchy manner, manager is there top level, junior managers are there, then supervisors are there under him, then field persons are there, then technicians are there. Hierarchy, there is hierarchy. In that way, we can arrange them in a tree structure, and tree is a subject matter of a graph. Okay, so before that, we should know what is a graph. It's a graph is a collection of edge sets and vertices. A graph is a collection of edge sets and vertices. E means collection of edges. Collection of edges. And V means collection of vertices. Collection of vertices. A graph is defined as G bracket E and V. E stands for collection of edges and V stands for collection of vertices. For example, this is a graph. This is a graph. According to theory, this is a graph. Here, how many edges are there? 1, 2, 3, 4. So edge set here is 3, 4 many. 3, 4. If you put a point here, then there are 1, 2, 3, 4. There are 4 edges. 1, 2, 3. How many vertices are there? 3. V1, V2, V3. So vertex set here is V equal to V1, V2, V3. So this is a graph. The name of the graph is G. It consists of 2, 3 vertices and 4 edges. Can I make a circle? Can I call this as a graph? Can I call this as a graph? Why? There is a single edge. I can say there is a single edge. But can I call this as a graph? No. Because there should be vertex. Compulsorily, vertex sets should not be empty. For a graph, vertex sets should not be empty. There should be at least one vertex. So if you put a vertex here, then it is a graph. According to theory, this is a graph. Just simple a circle, it is a drawing. Or drawing of a circle. But if you put a dot here, that is vertex, then it is a graph. Similarly, if I put a dot here, can this be a graph? I say this is V1 vertex 1. This is V1 vertex 1, edge is 1. There is vertex 1, edge 1. This is a graph according to definition. Suppose I put V1, no edges are there. Vertex 1 is there, V1, but no edges is there. Can I say this is a graph? Yes, this is a graph. That means edges may be empty. Edge set may be empty, but vertex set should not be empty. That's a graph. So this is called empty graph with one vertex. Empty graph with one vertex. Similarly, I can define V1, V2, V3, V4. This is also empty graph with 4 vertices. Empty graph with 4 vertices. Okay. That's vertices. There is a theory, degrees, degree of a vertex, we define D of a V. This is defined as number of, edges incident, incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of edges incident on the vertex. This is defined as number of incident on V. Vertex number of edges incident on vertex V is known as degree. So here in this graph, this is a graph name is there are vertex 1, vertex 2, vertex. There are three vertices. Edges E1, Edge 1, E2, Edge 3, E4, 3, Edge 3, E4, Edge 4. There are 4 edges and 3 vertices. So what is the degree of 1? Suppose I write it V1. V1, this is V2 and this is V3. So degree of V1, how much? That is the definition. Number of edges incident on V, that is the degree. So in V1, how many edges are incident? 1, 2, 3. So degree of vertex 1 is 3. Degree of vertex 3 is how much? There are 2 edges incident, so 2. Degree of vertex 2, how many? That is 3. That is 3. So degree, you know, degree means number of edges incident on a vertex, that is degree of vertex. So every vertex has some degree. Every vertex has some degree, and degree defined as number of edges incident on it. So application. We can apply graph theory to many problems. Application in application section, I can say Konigsberg problem. You know this problem? Name you know? Konigsberg. The problem name is Konigsberg problem. It is a very important problem in graph. Okay. Konigsberg is a place in Russia, Odisha of Russia. There are 7 bridges on rivers. 7 bridges on rivers. The problem is one has to start from one land place and covering all bridges once, he has to come to return to the same place. Whether it is possible or not, that is the problem. Okay, so it looks like this. Here, 2 bridges are there. Here 2 bridges. There is 1 bridge. 7 bridges. 1, 2, 3, 4, 5, 6, okay, 7. And these are rivers. A, B, C, D. These are rivers. On rivers, bridges are there. So there are 7 bridges. A, B, C, D are land area. A, B, C, D are land area, and 7 bridges are there. Problem is, you start from any land area. Suppose here, you start from one land area, then cover each bridge once. Suppose you start from here, you go to this, then to this, then you come this way, then come this way, then you come this way, and this way. Can you come to same place again? The question is no. If we want to return to the same place from where we started the journey, it is not possible. This problem is known as Konigsberg bridge problem. Physically, it is a place in Russia, okay, and mathematician Konigsberg has the place name is also Konigsberg. Invented this problem. How many, whether it is possible or not to reach from original place to same place? The answer is no. The answer is no. If you, how is possible? Now you make a graph of this. You map it into graph theory. Graph theory means 4 vertices are there, 1, 2, 3, 4. Suppose this is your B or D. Okay, between BD, there is a bridge. Between BD, okay, between AB, this is A and this is D. Between AB there is a bridge. Between BC there are 2 bridges. And between AC there are 2 bridges. Between BC, AB one edge. Between AD there is one edge. Between DC there is one edge. So you represent this problem into a graph. Taking land as nodes, as vertex, and bridge as a edges. Bridge as a edges. So it looks like this graph. Okay. If this graph is possible, and once you start joining from one vertex and come to covering each edges once, come to same vertex, possible, then this program has solution possible. Okay. So, but it is not a Euler graph. This is not a Euler graph. Euler graph means you start from one vertex and you have to come to the same place. Then it is possible. Okay. Euler graphs, if any vertex has even number, if all the vertices are of even number of degrees, then it is a Euler graph. Euler graph case it is possible. Okay. Here you see in this graph what is the degree of this? 3. 3 is a odd number or even number? Odd number. That means that criteria is not satisfied. That means all vertices are not of even degree. That means this is not a Euler graph. Representation of this conical bridge is not a Euler graph. If it is not a Euler graph, then from one vertex joining through all edges once, we cannot come return to them. That's why this problem has no solution. Okay. So this is the application of graph theory.